All right, welcome back. We're going to continue on with all of these matrices, and we're going to work with 8.5 operations with matrices. So the essential question today is, what operations can be used with matrices? Right? The first thing that I want to go ahead and look at is this box right here. Now, it's not necessary that you actually have to write every single thing down in here. Rather, I'm going to go ahead and explain what we're looking at just so that we understand all of the notation that they used. Right? So in all of our examples today, we're going to be talking about an individual matrix, and each individual matrix is going to be shown with a letter. So in this case, most likely A, B, or C, and those are going to be capitals. Then when we talk about the individual components or the individual terms inside the matrix, they're going to be referred to by the lowercase letters. So since here we have the capital A matrix, we're talking about the lowercase a term. So each individual one is a lowercase letter. Okay? And then in the third point, a matrix can be denoted by a rectangular array of numbers such as, and all of this is shown here. Basically, the first number that you see for each of these matrix terms is the row number. And then what you see here in that second number is the column number. So first one is row, second one column. Okay? So later on when we see something like A11, A21, that's what it's referring to. But really we're not going to use too much of the notation as we're just going to jump right ahead into the numbers. So again, you did not need to write any of this unless you wish to. Right? Now what you do need to write is this part. And we're going to be talking about matrix addition and scalar multiplication. And the idea of matrix addition is to combine two matrices together through addition. So if we have two separate matrices, A and B, and they have the same exact dimension, that's the most important point, they have to have the same dimension, then you can just add the two of them together as long as they are in the same place. So in other words, if we have A11, the top left number, and B11, right here, top left of its own matrix, then we can add those two numbers together, only those two, okay? And then right here, this note's going to be important. If you're adding two matrices that have different dimensions, so if this was a 2 by 2 and this was a 3 by 3, then we wouldn't be able to add them because they have different dimensions and that would be undefined, okay? So let's go ahead and do a quick example for matrix addition. So example 1. I'm going to go ahead and label a new matrix. Let's just make up one. A as 2, 4, 6, 8. And then B, we're going to have -1, 3, 4, and -2. Okay? And then for this example, I'm going to go ahead and add my two matrices. So if I'm looking for the sum of matrix A and matrix B, I'm basically going to be adding across. Okay? So I'm going to add this term and this term together. So I'm going to show my work. 2 plus -1. Over here, we're going to have 4 plus 3. Here, 6 plus 4. And then finally 8 plus -2. Okay, so after that, just simple addition really. 2 plus -1, 1, 4 plus 3, 7, 6 plus 4, 10, and 8 plus -2, 6. And there you go. That's matrix addition. If you can do addition, you can do matrix addition. All right? So setting that example aside, let's go ahead and jump to the next part, scalar multiplication. We're going to be referring to this term called the scalar. And the scalar is basically a number, a real number, that you're going to multiply an entire matrix by. You can think of it kind of like as a coefficient of the matrix, but again, the specific term is going to be called the scalar. So the definition of scalar multiplication, you're going to see all of this notation. I would recommend writing this down just so you understand the notation. But through the example, you're going to see that essentially we are just multiplying some number to each term of the matrix. Okay? So let's go ahead. Example 2. And my instructions are going to be to find 3a based on whatever a is. So in this case, we're going to have a be a 3 by 3 matrix. Let's go with 1, 0, 2, 3, 5, 6, and 5, 1, 6. Okay? And let's just throw in a couple negatives for the heck of it. All right. Now, in order to do scalar multiplication, what I would be doing here is basically rewriting this. So 3a, because that's what I'm finding. And then I would write the scalar right outside of the matrix, just to show my work. And then to further show the work, basically you can think of it as this 3 being distributed to each one of these elements inside the matrix. Okay, so to further show work, we're going to have 3 times 1, 3 times 0, 3 times negative 2, 3 times negative 3, 3 times 5, 3 times 6, 3 times 5 again, 3 times 1, and 3 times 6 again. Okay? Answer, 3, 0, negative 6, negative 9, 15, 18, 15, 3, 18. Okay? And that's scalar multiplication. All right? So nothing as intimidating as the last video, thankfully. And now let's go ahead. Looking at this next part, we're talking about scalar multiplication and matrix subtraction. In other words, we can also subtract matrices. And the whole idea is that you can use different operations at the same time. So we'll go ahead and use a smaller example just to show it. But example 3, let's say that we were asked to find 2a minus b. And then a is going to be 1, 0, 4, 3. B is going to be 2, 0, 1, negative 4. Okay. So to do this, I would rewrite it. Scalar 1, 0, 4, 3. And then minus 2, 0, 1, negative 4. At this point, I'm pretty sure you guys understand where we're going to be going. So only step I'm going to show is the distribution. So there's going to be 2, 0, 8, and 6, minus 2, 0, 1, and negative 4. At this point, you're going to subtract every single one of these terms. So over here, we end up with 0, 0, 7, 2. Okay? And there's multiplication and subtraction combined. Okay? And now, before we jump into the final 2 examples, I'm going to ask you guys to copy one more thing. Over here is the wonderful list of properties of matrix addition and scalar multiplication. It is pretty much identical to all of your properties from Algebra 1, except now it's applied to matrices instead. So go ahead, jot those down really quickly, and pause the video because I'm going to jump forward right now to the distributive property. And just like in Algebra 1, the whole idea of the distributive property is to distribute that coefficient, or in this case the scalar, to the entire matrix. What example am I on? I am on 4. Alright, so let's go ahead and do 4. And then instead of writing A and B, I'm just going to go ahead and write out the matrices here. 1, 3, 2, 8, negative 3. Let's go with negative 5, 6, 1, 0. And with this one, the idea of it is that we want to distribute the scalar into each of one of these matrices first. So we're going to have 4, 1, negative 3, 2, 8, plus 4, negative 5, 6, 1, 0. Okay. Distribute it. We get 4, negative 12, 8, and 32. Negative 20, 24, 4, and 0. I'm going to add these two matrices together because they are both 2 by 2 matrices, and get for our answer negative 16, 12, 12 again, and 32. Okay, no solving here. All we're doing is distributing and adding. Okay, final part, I promise. Example 5, we're going to solve equations that involve matrices. Now, solving equations that have matrices in them will pretty much involve all of the operations we've done so far, and then apply some basic algebra concepts where you're solving for a real number. So, for example, if we had like x equals a plus b, and I was asked to solve for b, I would just subtract a to both sides, and I get b equals x minus a. We're going to be doing the exact same thing here, except now instead of lowercase letters, we're going to be working with uppercase. So, in this case, if I were to ask what is b equal to, I would subtract the matrix A from x, so x minus a is equal to the matrix B. Okay, so a little bit abstract, but with this example it should be just fine. So let's go ahead and solve for x in the equation. And our equation will have, I'm going to keep things small again, negative 2x plus a equals b. Okay? And now what I'm going to do is also give you what a and b are, of course. Let's go ahead and keep it small this time. 1, 0, negative 2, 3. Negative 3, 2, 4, and 1. Okay? So instead of substituting my matrices in right away, the goal is to isolate the variables, so I might as well do that. So negative 2x plus a equals b. In order to isolate the variable, I'm going to subtract a, matrix A. Negative 2x equals b minus a. And then I'm going to not divide by negative 2, but I'm going to multiply by negative 1/2, just so that I'm sticking with the idea of using scalars. Okay, so x is going to be equal to negative 1/2 times b minus a, where the matrix is b minus a. Okay, so at this point, I'm going to substitute in negative 1/2, and then we have, let's see, it's going to be a lot of brackets, negative 3, 4, 2, 1, minus 1, 0, negative 2, and 3. Now, we could distribute this, but I think it's going to be easier if I just go ahead and subtract inside first, because technically I couldn't do that based on PEMDAS. So x is equal to negative 1/2, and then let's go ahead and subtract. So negative 3 minus 1, negative 4. 4 minus negative 2 is 6. 2 minus 0, 2. And 1 minus 3, negative 2. At this point, distribute that negative 1/2, or multiply, and I get positive 2, negative 3, negative 1, and positive 1. All right, and let me go ahead and pull that over. That is everything, okay? So all of these operations are what we can use with matrices. We've covered a good plethora of them. We do have one more operation to go over, but that will be saved for next week. So go ahead, rewind, replay if needed. Otherwise, move on to the Google form and have a wonderful 3-day weekend. Bye, guys.